Okay, so what we're starting to embark on today and tomorrow is really the development of the integral calculus. So if you think about what we've studied so far, we've studied about antiderivatives, and that was the whole problem. I'm sure you remember how we started off playing Jeopardy. The problem of finding the equation of an original function from that of its derivative. So I'm giving you the derivative, you're coming up with the original function. You're literally working backwards from when you've been finding derivatives so far this whole school year. So what we're turning to now is the problem of finding the area in a region in the Cartesian plane. Remember the Cartesian plane, that's your typical XY coordinate. We only deal in 2 dimensions. Yes, there is 3-dimensional calculus when you get to college. We don't have to cover that. So we're just dealing with your typical Cartesian XY coordinate plane. Now, it doesn't really seem like this would be very much related to the antiderivatives that we've studied so far, but probably by tomorrow you will see that it actually is very much related to each other. All right, so we're going to go way back in history. How would you find the area of a circle? But you have to pretend you don't know pi r squared, because pi hasn't been invented yet. You probably know it was sort of discovered, so to speak, by Archimedes. No date on that. I hunted high and low for that one, but we will be talking about Archimedes shortly. But pretend you don't know how to get area of a circle. This was definitely a problem actually the Egyptians faced. We know they were big into geometry as evidenced by their pyramids. But really anything very heavily geometry based, very much had its roots in Egyptian mathematics. So the question, and this is really actually a question that mathematicians grappled with. How do we get area of a circle? But you don't know what pi is yet, so you can't use that. So one option was to try to estimate the area of the circle by maybe inscribing known polynomials into the area. Alex, yes, there should be a new handout. Your facilitator should have it for lesson 4.3. So if we were to inscribe a triangle inside of that circle, well, that's obviously going to be a big underestimation. They knew how to get areas of polygons, of triangles, squares, rectangles, all those, hexagons, dodecagons. They knew how to get the area of any n-gon as far back as Egyptian days. So this is something they definitely could have done. But you can see that, it's definitely an underestimation. So the idea came about, okay, well, instead of using a triangle, what if we tried to increase the number of sides in the polygon? Or another idea, before I forget, was what if we tried to circumscribe a known geometric shape about the circle? But then obviously this is an overestimation of the area of the circle. So that doesn't do us much good either. So that's kind of when they had the idea of inscribing bigger n-gons inside of the circle. So you can see if you compare the underestimation provided by the square. So this is like how much under it would be. Okay, but compare that to what we had with the triangle when we used that. All right, it's definitely less than an underestimation when we use the square. So mathematicians figured that out pretty quickly, and they decided, okay, well, what if we kind of kept increasing the number of sides of the polygon that we were to inscribe inside the circle? They also kept fiddling with this idea of circumscribing about the circle, and then maybe taking the difference between the two. That might kind of get at what the pretty close approximation would be. So somewhere between the difference between an overestimation and an underestimation, the overestimation given by the circumscribing of a figure about the circle, and the underestimation given by inscribing a polygon inside the circle. Somewhere maybe in between would be the actual area of the circle. So that was another idea. They kept increasing the sides So here we have a hexagon. All right, they knew how to get areas of hexagons because it's really just a series of triangles, so they knew how to get that. And it's a little bit better of an estimation, but still not perfect. Again, they could figure maybe circumscribe the hexagon about the circle and then once again take the difference. And as they did realize that as they increase the number of sides, they're probably getting closer and closer to the actual area of the circle. So it was a great way to really estimate the area of a circle, but could you pinpoint it exactly? Not really. You know, it was sort of just the best you could do. So that led to something known as the method of exhaustion. The method of exhaustion was first verbalized by the Greek mathematician Eudoxus. Somewhere around 370 BC, a long time ago. He's really the one who first sort of, verbalized it and summarized it and how we can use it to estimate the area of a circle. And that's what it became known as, the method of exhaustion. Eudoxus was pretty much a early contemporary of someone who then came along soon after, who really formalized it in this diagram that you see here. You can see the circle right in here. Here's the circle right here. All right, and this is actually a copy of the diagram. You can notice at the bottom it does make use of some trigonometry, which again the Egyptians didn't know about. So by the time it made its way to Greeks, they knew basic sine, cosine, tangent, all that kind of stuff, and you can see that it gets used here. It's really the Greek mathematician, though, Archimedes, who really made a big contribution in terms of using geometric figures to, first of all, approximate the area of a circle. He also is the one who was able to verbalize how to get like the area of a segment of a parabola. He's the one who really made a lot of headway in formalizing a lot of formulas that we come to know today. So let's talk a moment about Archimedes. So, who knows the big story about Archimedes that you might have learned in chemistry class? Please unmute, because I have the chat minimized. Anybody remember? Oh, dude, you're missing out. Really? You don't know the story of Archimedes? Come on, he was like running naked through the city. Please unmute if you would, because I have the chat minimized. Okay, well, let's go talk about Archimedes then. Archimedes of Syracuse lived from about 287 BC. That part's not totally for certain. They didn't keep good records back then. But we do know he died, actually was murdered, in 212 BC. He was a Greek mathematician, a physicist, engineer, pretty much jack of all trades, astronomer, considered by most people to be one of the greatest mathematicians ever. He's one of these guys sort of up there with Da Vinci that people wonder about if his writings were to have continued and be found today. How far advanced more would we be technologically if all of his records had stayed around? Actually, a few years ago, if we ever get around to watching this in class, when was it, in the 90s, I think? 91, early 1991, actually a medieval prayer book was found, believe it or not, that once they started, really, investigating what was in there, because maybe you guys know, back in those olden days, when books were actually kind of scarce, they reused books a lot and the pages. So when they found this prayer book in 1991, they actually were able to uncover some of Archimedes' really early writings. And like I said, it's kind of up there with Da Vinci in terms of, what if his stuff had really been preserved as it should have been. We sort of wonder how far more advanced could we be today. But anyway, Archimedes, he lived on the island of Sicily off, here's Italy up here. This is Italy. Okay, Rome would be like all the way up here. It's not on the map. Okay. But this is the island of Sicily that you see right here. He lived here in the town of Syracuse, so he lived basically at the beach. Lucky guy. He didn't have an easy life, though, because basically during most of his life, there was a war going on. Actually, the Punic Wars. First Punic War was from 264 BC to 241 BC. Maybe you guys remember your history. Punic Wars were between mostly the Roman Empire. You had Greek involved, and Sicily, or not Sicily, Carthage. Carthage would be over here. You sort of see part of the, Carthage would be over here. I guess that would be Africa it's on. So poor Sicily was kind of caught in the middle because it had Carthage on the west coast. It had Romans sort of to the north and east. It had the Greek Empire over here to the very far east. So Sicily was really caught in the middle of all this war going on. At first, Sicily aligned itself with Carthage, but then a treaty of alliance was forced upon Syracuse's king, Hiero II, by the Romans. And so they kind of end up jumping alliance to the Roman emperor. So Sicily was very much caught in the middle of all this. So how Archimedes played into this is that Archimedes was King Hiero's military advisor. He was in charge, so Archimedes was the one in charge of defending the coastal defenses of the town of Syracuse. As you can imagine, as a port city during wartime, you can figure out the rest. Sort of an important place to be. So, that's kind of how Archimedes got involved in all this. So that kind of brings us to the cool story I was wondering if you knew. Because think of Archimedes as being, he was like the mathematician to the crown, okay, to the throne. So basically what happened was, so King Hiero, who Archimedes essentially worked for, King Hiero had a crown made for himself. And he kind of had suspicions that the guy who made it did not make it of pure gold. So basically he got robbed. He thought it might have some silver in it or lead or something else, so it wasn't pure gold. So he asked Archimedes to kind of look into it. But the catch was, of course, Archimedes couldn't just simply melt down the crown to find out, because that would sort of destroy the king's crown, which he didn't want to have happen. So Archimedes had to get creative and figure out this other way to determine if the crown was pure gold or not. So as the story goes, Archimedes was in the tub one day taking a bath, and he figured out that an object would displace an amount of water equal to its own volume. So he knew if he could take the mass of the crown and divide that by the volume of water that it displaced when he put the crown into water, he should be able to figure out the density of the crown. And if it was of cheap gold, or maybe not solid gold, the density would be lower than the known density of solid gold, because they did actually know what the density of solid gold was. Okay, that was known. So apparently, as the story goes, when Archimedes figured all this out, he jumped out of the tub and ran naked through the town of Syracuse, yelling Eureka, which is Greek for "I have found it." So as it turns out, by the way, the crown was not made of pure gold. It did have silver mixed into it, so yeah, that guy kind of got in trouble. So that's the cool story about Archimedes that I thought you... So we know this principle today as Archimedes' principle. You probably learned it in chemistry, or the law of displacement. I think that's where I remember learning it, was in chemistry class. So back to the wars. So it was around 218 BC that the Second Punic War broke out. I'm sure you've all heard the story of Hannibal. Well, Hannibal was a Carthaginian, I guess that's how you pronounce it. He was from Carthage, okay, so he was on that side, okay, remember the map. All right, so Hannibal's from over here, okay. And you've probably learned the story of Hannibal crossing the Alps into Italy. So that happened, somewhere around that 218 to 17 time frame. And it was at that point that Syracuse and all of Sicily pretty much started questioning its allegiance to the Roman Empire, because thinking, well, okay, it kind of looks like Carthage is winning the war at the moment. So why did we go with the Romans again? So they all started questioning that. So at that time, Rome sent Marcus Claudius Marcellus to Sicily to pretty much win them back and, quell all the little, riots going on and all that fun stuff. And he pretty much laid siege to Syracuse starting in the year 213. All right, so notice that's a year before Archimedes died, okay, because that kind of ties into it. They pretty much held the city or tried to take it over for about a year because remember, Archimedes was King Hero's military advisor, and as a pretty darn good engineer, mathematician, physicist, etc., as you can imagine, the town of Syracuse was pretty well defended. So it took about a year at least for the Romans to really take over and take control of the city. So Marcellus' siege pretty much failed after a year. They decided to blockade the city. Remember, it was a port town, and kind of starve out the people, essentially. And it was in 212 that Marcellus basically caught the Syracuse people off guard because they were essentially partying. And this was during a festival to the goddess Artemis, and they were kind of hooping it up and having a good time. Think Mardi Gras, okay? Think along those lines, okay? So Marcellus kind of took advantage of the fact that everybody was partying and not really paying attention to what was going on with the war, and he basically took the city over. His soldiers, his Roman soldiers, were given one day to loot the city and pretty much ransack the whole town. And it was during that time that Archimedes was killed. As the story goes, Archimedes was working on the beach in the sand. That's where he did his work. It's like a big blackboard, right? The soldiers told him to get out of the way, and he wouldn't, basically. And so became those famous last words, noli turbere circulos meos, which is Latin for don't disturb my circles. And with that, the soldiers basically killed Archimedes. Marcellus was actually not happy because he had given an order that Archimedes not be killed because he was so, basically his brain was so valuable. And the Roman Empire knew this. They did not want him killed. They kind of wanted to be able to employ him themselves. So when Archimedes was killed, the soldier who actually killed him was then treated as a murderer and was put to death. Archimedes was buried with full military honors and his family given pretty much a nice little payoff. But that's how highly regarded he was. And so he really came to a very premature death of sorts. And as I mentioned before, we kind of wonder if his works really had been preserved or if he hadn't been killed. What might we know today that, maybe we're just learning now that maybe we could have learned, decades, centuries before. So it's kind of a really interesting story. So that's why I like this topic. You get some cool history stories. All right, so let's kind of go back to where we were. All right, so we're going to fast forward a little bit. 16th century, 1500s. Now you have to think about what happened between the time of Archimedes and the 16th century. Think of your history. Who remembers what happened in there? Please talk. I don't have the chat window open. I don't think your history teachers would be very happy. All right.
Yeah.
What'd you say?
Did Newton come up with his stuff?
That was 1700s.
Okay, never mind then.
That's all right. It's a good guess. We're getting there. We'll get there tomorrow. What else has happened history-wise in between like 200 BC and like 16th century, 1500s? What else is going on in there? None of you took AP European history. Where are you people? You should know this. We haven't quite hit Newton yet. Well, if you think of your history, all right, we're talking fast forwarding to the 1500s, the 16th century. Remember, Rome fell in 476 AD. That pretty much started the Dark Ages around the 5th century. Dark Ages went on for a long time, all right, and you have to remember what happened during the Dark Ages. Nothing. It was like a intellectual void of nothingness. Nothing went on until finally people decided, you know what, this has to change because we're not getting anywhere. Renaissance, 14th century, 1300s. Renaissance pretty much lasted from the 14th century to the 17th century. And it was at the end of that Newton came along. All right. So this is kind of the historical context in which you have to start thinking of a lot of this happening. So given that during the Dark Ages, nothing was happening really of value at all except plagues, you know, and I guess the Crusades were in there somewhere too, but just lots of death, famine, disease, stuff like that. Nothing worthwhile intellectual-wise was going on until really, you know, people started to wake up, literally, and decide, you know what, we got to start getting our butts in gear again. So it's really with that mathematicians, especially in Europe, really started, you know, taking advantage of this. You know, we all know Renaissance, the word means awakening. And that's really what it was, because mathematicians started actually coming out of the woodwork again, working on things, brainstorming, starting with the works of Archimedes. All right, and this is what it turns into. All right, so remember, Archimedes had really formalized a way to try to estimate the area of a circle. So what mathematicians, when the Renaissance came about, wanted to do was, well, how would you find the area under a curve? All right, so think of the Cartesian plane, the xy plane. And they wanted to figure out, okay, well, could we apply what Archimedes did and that method of exhaustion to finding the area under a curve? And what they came out with was, yeah, we could do that. What if we put rectangles underneath? Just like, you know, days of yore, they had put polygons inside and about a circle. They thought, well, couldn't we do kind of the same thing with a curve? So they had the idea of inscribing rectangles underneath a curve, because heck, they knew how to get areas of rectangles. But once again, just like we saw with circles, you do end up with a lot of underestimation, okay? And that's all this empty space here that you see, okay, that these arrows are pointing to. We refer to that as negative error. Okay, you're going to need to know that at some point. Okay, so the fact that it is an underestimation really does lead to quite a bit of negative error. So then, just like mathematicians before, they're like, okay, well, instead of inscribing rectangles under the curve, couldn't we circumscribe them outside the curve? All right, and then obviously we end up with overestimation because you have these little rectangles kind of jutting outside the curve. That's what we refer to as positive area. So just like mathematicians back in Archimedes' days started figuring, okay, well, couldn't we subtract the two and maybe come up with a pretty decent approximation? Absolutely you could. All right, so they really just took what Archimedes and Eudoxus and other mathematicians from, 200 BC had done and took it a step forward, all right, to now applying it to finding the area under a curve. All right, so what this led to really were different types of approximations. And this is where we'll soon be turning to your graphing calculator programs. We could have inscribed versus circumscribed rectangles, either under or outside the curve. We could talk about a left endpoint approximation, a right endpoint approximation, and a midpoint approximation, depending upon exactly how we fit those rectangles under the curve. And these are just three ways. I mean, they're not the only three ways. There are other ways to configure or use rectangles. These are just three of the ones that we're going to be focusing on, these three. And depending upon the type of approximation we end up using, that's going to either lead us to having either inscribed rectangles or circumscribed rectangles. All right, so if you guys have your calculators handy, there's two programs in particular that we're going to be working through. There's a couple problems on your handout, and we'll be talking about how to really use these programs, also write it out by hand. The first program, it's called IntMaths. If you take a look under your calculator programs, you'll notice they're all alphabetized. IntMaths, what that does is gives the values of the left, right, midpoint, trapezoidal, and Simpson's approximations for areas under a curve. Trapezoidal and Simpson's we'll be getting to later, excuse me. Today we'll be talking about the left, right, and midpoint approximations. Another program that you have there is simply called area. That was really good for us visual people, because what that will do is actually draw out the thing for you and then give you the left, right, and midpoint approximations for the area under the curve. All right, so we're going to be playing with these as we actually do the practice problems. Okay, so you should have these on your handout. And the first one we're going to look at, and I have my graphing calculator up here, so you guys will see, exactly what you should be seeing on yours. All right, so this is the first one we're going to tackle. Find the approximations for the area under the curve y equals sine of x. We're just talking about the interval from 0 to pi over 4, or pi over 2 rather, and we want to use 4 subdivisions. All right, now what that means when we say 4 subdivisions, think 4 rectangles, okay? So what we want to do is graph this on our calculator. I do have a nice window that will work for us pretty well. So let me switch back to the calculator. Oh, I just had it. There we go. All right, so if you go under y equals, and we'll clear this out, we'll just graph sine of x. Hang on, I don't think you can see this yet. Hang on a sec. It hasn't come up. There you go. Now I think you should be seeing it now. Okay. So we'll just go ahead and graph y equals sine of x. Like I said, I do have a nice window since we're just trying to find the area from 0 to pi over 2. So we'll just go ahead and use that as our x's under our window. So let's do 0 to pi over 2. For our interval, let's do like pi over 8 for our scale. And then for the y's, I have a nice one for the y's. A negative 0.25 up to a positive 1.25. And maybe we'll do a scale of 0.25 for that. Okay, so if you go ahead and set up your window like this. All right, and then let's go ahead and graph it. All right, so that's the part of the sine curve, and all you're looking at is we want to find, the area under here in the first quadrant from 0 to pi over 2. Okay, obviously you can see it's kind of like a part of a circle. It's almost like a, if we were to do it all the way out to pi, of course, that's going to be a semicircle. So you could even try to use, some of the definitions of area of a circle to try to find this and approximate it. But this, our focus is sort of using this instead. Okay, so let's do the area program first. Okay, so what you want to do from your graph, just hit your program button, and it's probably that very, very first program, area. So just hit enter on that, and hit enter again. It's going to first ask you for the endpoints between which you want to find the area. So in this case, that's going to be 0. Then you just hit enter, and pi over 2. And I do hope you're doing this along with me to make sure yours works, because we have had it happen that in me transmitting the programs to some people, if they don't take right, now would be the time to figure it out. Okay, so if you really do need to be doing this along with me to make sure your program works. Okay, because like I said, it has happened that sometimes something just gets messed up in the transmission when I was downloading the programs to your own calculator. Number of subintervals are going to be 4. All right, so once you have that all set up, just hit enter. All right, and notice it goes back to your graph, and notice what it's drawn for you here. It's drawn 4. There's actually a 4th rectangle. It's really just has a height of 0 right here. But you can see the other 3 rectangles. And you'll notice the little wormy thing in the upper right corner of your calculator screen. That means it's still working. All right, what you're looking at here is a left endpoint approximation. Now let me tell you why it's a left endpoint. All right, notice how it's the upper left corner of each rectangle that hits the curve. That's what makes it a left endpoint approximation. All right, the reason you need to know this is because you're going to have to draw these at some point, and you'll be told what type of approximation you need to draw it as, and you need to know how to draw it. Sometimes you won't have your calculator to look at. All right, these have shown up on the AP exam in the non-calculator part. So you need to know how to visualize these yourself. Okay, so this is what we refer to as a left endpoint approximation because the upper left corner of each rectangle is touching the curve. Now I said, there's another rectangle. It's really flush to the x-axis down here. The left corner is really hitting the origin, and it has a height of 0. Okay. Now, as I mentioned, you should notice this little wormy vertical line kind of moving in the upper right corner of your calculator. That means your calculator's still working. So if you hit enter, notice there is your left endpoint approximation. So you'll want to jot that number down. Usually when we're doing this, we'll take it out at least 2 thousandths. I would not recommend writing down the entire decimal. The AP people hate when you do that. We hate when you do that because that tells us the student does not know how to round appropriately. So I would recommend probably 4 or 5 decimal places. The reason being you're going to need that many decimal points, the decimal places, to notice the subtle differences between some of these approximations. Okay, now you'll notice the little wormy thing still going in your upper right corner of the calculator. Hit enter again. Goes back to the graph. What it's going to draw for you now is the right endpoint approximation. So now you can actually see all 4 rectangles. And notice how it's the upper right corner of each rectangle hitting the curve. All right, but as you can also tell, notice how these rectangles are kind of jutting outside the curve. This is one that's going to result in positive error. It's an overestimation of the actual area under the curve. All right, so hit enter again, and you can take note of what the right endpoint approximation is. All right, now you'll notice your little wormy thing still going. So hit enter again. The last one it's going to draw for you is the midpoint approximation. This is usually considered a nice balance between the right endpoint and the left endpoint approximations. Is it actually the quote-unquote average, the mean of the two? No. It's going to lie in between the two, but you can't just, take the left endpoint approximation, add it to the right endpoint, divide by 2. That is not necessarily going to give you your midpoint approximation. Okay. You'll notice that the way in which these rectangles are drawn, it is the midpoint of the top of each rectangle that is hitting the curve. This is the one that's going to really end up being a very nice balance between positive error and negative error, because notice what you have with this, for instance, second rectangle here. Notice you have it jutting out a little bit there, but then it's underneath here. And notice how those two areas are almost equal to each other. They almost offset each other. All right, same thing with the first rectangle. All right, this positive error here in the very far lower left kind of offsets the negative error that results kind of just butting up against that second rectangle. All right, so the midpoint approximation is often, of the 3 approximations, the midpoint is typically the closest to the actual area under the curve. All right, and you can see that that's your midpoint approximation. Notice again, it does fall in between the left and the right endpoint approximations, but you can't just average the left and the right together. All right, so as I said, the area program's really nice because it really does provide you with that nice visual. Let me show you the IntMeths program. That's for those of us who don't care what the graph looks like, we just want the answer. If you go down to the IntMeths program, there we go. All right, and you go ahead and run that. It is going to prompt you first for the endpoints of the interval again. So that would be 0 to pi over 2. It's going to ask you for n, which is the number of subintervals. And when you hit enter now, notice it just spits out the answers, no pictures to look at. But notice how they are the exact same decimal values as we obtained from the area program. All right, so, there's no difference in the actual answers it gives you. The only difference is you don't have the visual. of what it looks like. You'll notice your wormy thing's still going up there. If you hit enter again, there are a couple more approximations it's going to give you. The trapezoidal rule, which you can see the way in which it's calculating that is by doing what I said you don't want to do for the midpoint, is just average together the left and the right endpoints. That's a very rough estimation of the trapezoidal rule. The trapezoidal rule is one that you will be learning by hand later on at the end of this unit. It is one that often shows up on the AP exam. And basically it makes use of trapezoids instead of rectangles. Okay. The last one is the one we know as Simpson's rule. We'll talk about that when we do trapezoidal rule, but you don't actually have to know how to do it by hand. And be thankful for that because it's a mess. But we will talk about it and where it comes from. Basically, if you imagine doing a rectangle under the curve, but instead of the top of the rectangle being flat, that they're parabolic shapes, like segments, arcs, that follow the shape of the curve. Simpson's rule is said to be the most accurate approximation for the area under the curve. All right, one other thing to notice is these approximations are not using calculus at all. They're using basic geometry. All right, area of a rectangle, add up the areas. That's all it's doing. So that's one really big thing to understand about these. These are what we refer to as numerical approximations for an area under a curve. They are not making use of calculus at all. Remember when all this was going on with mathematicians in the 1600s, the calculus had not yet been discovered. So they didn't have anything like that. All they knew was basic geometry. All right, so that's one really big thing to keep in mind about this, is this very much predates what you're doing now. It predates the discovery of the calculus and the way that you're going to soon be learning to use calculus to find the exact area under the curve. Okay. All right, let's go back. Let me stop sharing for a minute. We're going to go back and take a look at that second problem. Like I said, if any of you have questions, please speak up. Again, I have the chat box minimized, so I'm not looking at it. So please do speak up if you have a question. All right, so now we're going to take a look at a different type of function, but same idea. So now we're talking about the rational function 8x over x plus 1. Let's see, we're talking about the region bounded by x equals 0, x equals 4, y equals 0. So y equals 0 is the x-axis on the bottom. We want the lower sum, upper sum, and midpoint rule sums of the area under the curve. Now notice they don't tell you left endpoint, right endpoint. When they talk about lower sum and upper sum, you need to figure out which is of those is the left endpoint approximation, which is the right endpoint. Okay, midpoints, well, that speaks for itself. But the other two, between the lower sum and the upper sum, you're going to have to figure out, which is the left endpoint and which is the right endpoint, depending upon how the function looks. All right, so we're going to go back to the calculator, and we're going to go ahead and graph this one. Once again, I have a nice window we can use. Under y equals, oh, you got to stop this. Remember, anytime you want to stop a program, because sometimes you actually have to break out of these programs, if you just hit your on button, that's how you can quit a program, okay? Because sometimes these programs will keep running, and you actually have to break out of them, okay? So that's one thing to keep in mind. All right, so if you go under y equals, let's see, we want 8x. Don't forget your parentheses, be mindful of those. Divided by x plus 1. And we want, let me set up the window for you. If you go under window, we're going to do a window of -1 to +5. And we can just do 1 for our scale. Make it easy. 1 at 5. There we go. And our y's, we're going to do -2 to +10. And we'll do 1 for a scale of that one also. Okay, so if you hit graph, this is the part where, now remember, if you go back to the problem and read where they wanted you to find the area in between.
Okay. Hey, Miss Henderson.
Yes?
We can't see what you're doing with the calculator. Like, it's kind of frozen.
That might be something on your end. Hang on, let me stop sharing it and come back.
Okay.
Thanks for letting me know. Appreciate it.
You're welcome.
Did it come back now? Is that better?
No, it's still stuck on that where you were typing it into Y1.
Is it? Okay.
It's stuck there for me too, Miss Henderson.
Okay.
Me
Claire, I think
three.
that was your voice. Okay. Hang on. Yeah, you just got to break out of it. All right, are you back to the PowerPoint now?
No.
No? Did that bring it back to the PowerPoint?
No.
No? Okay. Should have synced it up for everybody. Let me see. Hang on.
It's better for me.
Okay. Is that back to the PowerPoint now?
Yes.
Yes? Okay.
It's working. Thank
Okay.
you.
No, thanks for letting me know. I appreciate that. Thank you. Sometimes it just gets stuck when, especially doing it from home and you have so many windows open. All right, so let me go back to the calculator now, and hopefully this will work. There we go. So you seeing the calculator now on the graph okay?
Yes.
Okay, do you guys need the window again? Did you need to see that again?
I don't need it.
Okay, I didn't know if anybody else did. Okay. So according to the directions, remember what we wanted to do was find the area under the curve from 0 to 4. Okay, now notice this is going out to 5. Okay, I just did that so we kind of have a bigger picture to look at. Okay, so once again, we're going to go ahead and just run the area program. All right, this way we can actually look at the rectangles and figure out, you know, between the left and the right endpoint approximations, which is the lower sum, which is the upper sum. So let's go ahead and run that. They want us to use 10 subintervals, notice. So A would be 0 in this case. B would be 4. And number of subintervals is 10. So as you can imagine, we're squishing 10 little rectangles under that curve. So it's going to be a little squishy. There you go, but you can count them. Again, the very first one is sort of flush to the axis, to the x-axis.
Miss Henderson?
Yes.
I was wondering how you got 10 subintervals.
It says that in the problem.
It says...
Hang on, let me go back. Yeah, under the curve using 10 subintervals.
Oh, it doesn't say that on my sheet.
Oh, it doesn't? Oh, okay.
It doesn't say it on mine either.
Oh, sorry. 10 subintervals. Add that in. Sorry. Don't know why it wouldn't. I copied it from the PowerPoint. Okay. Yeah, you'll have to be told how many subintervals. On the rare occasion you're not, you can make up your own, and that would be fine. But typically you're going to be told. Okay. But again, the first rectangle is actually flush to the x-axis down here. But otherwise you can see there's 9 other rectangles. okay? So looking at this, if you take a close look, notice it's the upper left corner of each rectangle that's hitting the curve. So this is the left endpoint approximation. Now remember, they identified it as the lower sum and the upper sum. All right, notice all this white empty space. All right, this is obviously going to be an under approximation, so this is what we refer to as the lower sum. All right, so in this case, the left endpoint approximation corresponds to the lower sum. All right, that's one thing you would have to take note of. Depending upon the configuration of the curve, it's not always going to be the left endpoint that is the lower sum. It could be the other way around. Okay, so hit enter, and you can take note of what you get for here. So about 17.7437-ish. And you'll notice your little wormy thing still working in the upper corner. Hit enter again. And once again, it's going to draw 10 rectangles, and you can count them, and there are indeed 10. If you take a look at it, you'll notice it's the upper right corner of each rectangle that's touching the curve. So this is your right endpoint approximation. And notice how you have these rectangles jutting outside the curve. All right, this is going to be an over approximation for the actual area under the curve. So this is what we refer to as the upper sum. All right, and if you hit enter, all right, notice it's definitely bigger than the lower sum was. Hit enter again. Now it's going to draw for you the midpoint approximation, and if you look close, you'll notice it's the midpoint of the top of each rectangle that's hitting the curve. You can really see it on these first few rectangles. Okay, hit enter again, and you'll notice that it is in between the left endpoint and right endpoint approximation, but by no means is it the average of the two, but it does lie in between. Okay, so that's pretty much how you run the programs, and you'll have many occasions to use these in the homework. You're going to see these in the AP exam. These are programs that the College Board just assumes that all calculus students have. You'll notice even in the multiple choice, they'll give you a problem like this and say, find the left-hand approximation for the area under the curve. And it typically, often will be on the calculator part. You're welcome to just use your calculator to do it. Because they really truly do assume that students have these programs. And no, they don't erase the programs. That would be horrible. Okay, so let me go back. Let's see, we got about a half hour left. All right, so the next thing we're going to talk about is a really, really, really big idea called Riemann sums. If you could vary the widths of the rectangles. So if you take a look at the rectangles we did before, they were all the same width. All right, and you can even take a peek at your calculator again, and you'll notice they are all the same width. Of the rectangles, they're all identical. So the question arises: okay, well, couldn't we maybe get a better approximation if instead of having those rectangles all be the same width, if maybe we could vary the width? And this way we could squeeze some skinnier rectangles in there to take up some more space and, really just vary them so that we can fit more under the curve and thereby minimize how much either positive error or negative error we have. All right, and this is the idea of a Riemann sum. That's how you say that word. Riemann, that is a guy. Okay, we'll be talking about him soon too. But that's how you say Riemann. So it's a Riemann sum that really uses this idea of the summation of the area of rectangles, but it allows the width to vary. All right. The width of the largest rectangle, the fattest rectangle, is what we refer to as the norm. Right here. All right, and it has its own symbol. It kind of looks like a double absolute value bar with a triangle in the middle. That's what we refer to as the norm, is the width of the widest subinterval. So if you think about it, all right, as that width approaches 0, you should be able to fit in more and more and more rectangles. So therefore, as the norm approaches 0, the number of subintervals n approaches infinity. all right? Because as that fattest rectangle gets skinnier and skinnier and skinnier, you're going to be able to fit more and more rectangles in there. Hopefully that makes sense. All right, so here's a picture of what we're talking about. Okay, you'll notice some of these rectangles are a little fatter, like this one right here. That one's kind of fat. But here's a really teeny tiny skinny one right there. There's some in between, like these two over here on the right. Here's some more skinny ones over there. But that's what we mean. If we could maybe, make some of these rectangles skinnier, we might even be able to fit more in. Like maybe this fat one here, even if we broke that up, maybe this fat one right here, maybe if we split it up a little bit more, like this, then actually, there you go, you can even minimize that, negative error a little bit more, because now instead of that big white part, the only error you have is right here. All right, so really by varying the widths of the rectangles, you really do get to minimize that negative error. Okay, so I mentioned this was named for a guy. It's named for Georg Riemann, German mathematician who lived from 1826 to 1866. Notice the dates during which he lived. It was after the Renaissance, like about 100 years after. So he did live after the discovery of the calculus in the 1700s by Newton and Leibniz. We'll be talking a lot more about that tomorrow. And there is an actual formula. Now, you're not going to have the formula memorized. You're going to need to know how to do the problems. And we're going to do one or two of them today, and then that's probably where we'll stop. You just need to know how to do it. But I know you know all how to find area of a rectangle, so I am very confident you know how to do this. All right, so the way in which you calculate a Riemann sum is, all right, we have the Greek letter sigma. It is not an E, it's the Greek letter sigma. It's a summation symbol. All right, hopefully you guys studied summations in either Algebra 2 or Pre-Calculus. And in this case, you're doing the summation from 1 to n. All right, now remember, n is your number of rectangles. Okay? So you're doing the summation from 1 to n of f of c sub I. So this whole part, that's your height of the rectangle. Basically, you're going to go one rectangle at a time and do width times height plus width times height plus width times height. The height of the rectangle is always coming from the function value, hence the f of x notation, okay? Because the height of the rectangle, remember that rectangle is going to be hitting the curve someplace, so the height of the rectangle is always coming from the function itself, okay? The width, that's what we refer to as your delta x. I know you've seen that in other things so far this year. So really, literally what you're doing is going one rectangle at a time. Width times height plus width times height plus width times height. And you just have to remember the height you're getting from the function. That's it. It looks more horrible, but, it's pretty easy. So as I mentioned, Georg Riemann, he was a German mathematician. He actually did a lot of work in physics. And his mathematics actually became the basis for Einstein's theory of relativity. Little side note. Good Jeopardy question, right? So Riemann did a lot of little things in mathematics. Nothing huge. He didn't discover the calculus. But this is one of the big things named for him. Because he's the one who really formalized this idea of using varying widths of rectangles in order to approximate the area under the curve. Which is interesting, he did that because the calculus had already been discovered when he came along, although it had not yet gained wide acceptance, which we'll talk about tomorrow. So it's interesting that this particular little piece is named for him. You would have thought it maybe would have been better named for somebody like Archimedes or somebody like that. But that's okay. We like Riemann. He's a cool dude. So we'll go with him. All right, so here's a typical Riemann sum problem. And then, like I said, I think we'll do one ourselves. And we'll actually use this for our example. And And then maybe if we have time, we'll go back and do one of those that we did in the calculator. As I said, it looks worse than it really is, okay? The idea with a Riemann sum is, and this is a good example, this is the curve 10 minus x squared. Okay, that's the red curve that you see here. Right, this is 10 minus x squared. Okay. If you take a look at the little paragraph there, you're trying to find the Riemann sum on the interval from 0, so here's 0, up to 3. Here's 3. Okay, this is 2. Here's 1. At the given values of C. So pretty much what they're doing is telling you where to use your rectangle, okay, and how to set up your area of a rectangle. All right, so notice how many rectangles we have. We got 1, 2, 3, 4, 5. All right, so basically we're just going to go one rectangle at a time and find the areas and add them up. Okay, the notation that you see here is notation you should get used to, because this is how you're going to see it in college textbooks. It looks like a jumbled mess, but it's really not that bad. Okay, so let's just start with the first rectangle. Okay, and we're going to go ahead and calculate the Riemann sum for it. Let me change my pen color really quick. Okay. All right, so remember the way in which we're going to approximate, hence the approximately equal to symbol, is basically doing the summation of all the areas of the rectangles. Okay, this is what this is telling us. All right, so that's going to be approximately equal to, you can do the squigglies, remember. All right, so let's go do the first rectangle. All right, the first rectangle goes from x0 to x1. All right, x0 is 0, x1 is 1. So that has a width of 1. Okay, so our width is 1 times the height. Now notice the height we're getting from this c sub 1 value. All right, and where that hits the curve. All right, now look at your little legend over here. You're told c sub 1 is 0.5. All right, so the way in which we're going to get the area of this rectangle, it has a width of 1, a height of the function value at 0.5. And I'm going to show you a shortcut, easy way to do this in your calculator. All right, so we got width times the height is going to be given by the function value at 0.5. All right, so that's your first rectangle. Okay, 1 is the width, the function at 0.5 is the height. So that's rectangle number 1. Plus, now we're going to go do rectangle number 2. All right, second rectangle goes from 1 to x2. What's x2? x2 is 1.5. So 1 to 1.5, that has a width of 0.5. All right, so 0.5 is the width for that. Times, now the height's going to be given by the function value at, all right, see the green line? So let's see, that's C2. What's C2? C2 is 1.25. So we want the height at 1.25. What you're doing right here, this is what you actually end up doing. You're going to do this in the homework. You'll see this in the AP exam. This is exactly how you set it up. You need to set it up by hand, but it's then fine to just do all the work in your calculator. All right, so that's your second rectangle. All right, now we got the third rectangle. All right, that's the really, really skinny one. That goes from x2 to x3. So x2 is 1.5, x3 is 1.75. So that only has a width of 0.25. That's a really skinny one. And the height, let's see, where are we getting the height from? The height, notice, is this right endpoint where this green dot is. All right, that corresponds actually to x3 and x2 or x3 and c3 are the same number. So what's that? 1.75. So the function value at 1.75. All right, if anybody doesn't see how I'm doing this, please do let me know, okay? Just holler. All right, so we got 3 rectangles done so far. All right, fourth rectangle's going from x3 to x4. So that's 1.75 to 2.25. So that's a width of 0.5. All right, so our width's 0.5 there. And the height we're going to get from, let's see, that's rectangle 4. All right, so here's the green dot. It kind of looks like a midpoint thing. So that's C4. So what's C4? 2. So the function value at 2. All right, one last rectangle to go. All right, so the last rectangle is going from x4 to x5. So that's 2.25 to 3. So that has a width of 0.75. And the height we're getting from, it's a little off center right here. We're getting the height from C5. So what's C5? 2.75. Okay, so that's the number crunching we have to do. All right, so let me show you how you can really easily set this up in your calculator. You're pretty much going to let the calculator do all the number crunching. It saves you the bother of having to do all of these individually and having, kind of rounding off a lot of values and ending up with a lot of round off error. So let me go back to the calculator. All right, let me clear all this stuff out. So basically we want to take that big thing and just type it in. All right, so go under y equals if you would. Remember what our function was. It was 10 minus x squared. All right, so go ahead and have that under y equals. And what we're really going to do is make big use of that function notation that our calculator will do for us. That we've talked about before. I've always said you're going to be using this a lot. This is where you use it. All right, so if you go back to your quit screen, and we're just going to kind of type in exactly what we just had. All right, so the first rectangle, remember, had a width of 1 times, and then remember the height was given by the function value at 0.5. So remember how we talked about you can pull up your function notation? If you do vars and over to y vars, and then the first one is function, all right, it really just mimics that f of x notation. All right, so what you just typed in is 1 times f of 0.5. And we're just pretty much going to type in that whole long thing that we just wrote out. So that was your first rectangle, plus second rectangle, remember, was 0.5 wide, times the height was given by the function value at 1.25. So you want to pull up y vars, y1 at 1.25, and hopefully I can do this without having any typos. So that's your second rectangle. Plus third rectangle, remember that was the skinny one, so it had a width of just 0.25, times the height was the function value at 1.75. Plus, all right, now your fourth rectangle, this is the one that was 0.5 wide, times the height was given by the function value at 2. Plus, and finally the last one was the one that had the width of 0.75 times the height given by the value at 2.75. All right, compare your answer to mine. Hopefully that's what you get. All right, and all of us should be getting the same answer, assuming we all did it this way. The reason this is the ideal way to do it is, again, you're pretty much cutting out any round off errors, all right? Because a lot of people think, well, can't I just do a table and type in, like, the 0.5, the 1.25, the 1.75, the 2, and the 2.75 and use all those values? Well, you could, But, assuming you're just copying them over from the table, you're going to have a lot of round-off error. All right, this pretty much minimizes it for you because since the calculator's doing all the number crunching, it's preserving all of those decimal values. All right, so this is what we refer to as a true Riemann sum. All right, so hopefully, did anybody not get the same answer I did? It might just be due to a typo if by chance you didn't get it. Okay, so let me go back. See, I know we're running short of time. So basically what we'd have now is our answer from this would be about 20.53125. Okay. Notice the approximately equal to symbol. That's really the important one, is that one right there. You can do it with the 20.53125. But since that is the exact decimal you got from all that stuff you just typed in, it's not as critical as the other one. The other one, though, is really important. Okay. So let's maybe go back and take a look at one of those that we did in our calculator. Maybe, let's see, let's go back to maybe that sine one, because that was pretty short. That was only 4 subintervals. This one.
Miss Henderson?
Yes.
My screen's frozen again.
Is it frozen again? Okay.
It works now.
Okay. Sometimes, yeah. I don't know whose end that happens on. I have no idea. Thanks for letting me know. All right. So we're going to go back and talk about how to do this one by hand. And we're going to do it as a left endpoint approximation by hand. Okay. So one thing we could do is draw the curve. All right. If you need to graph it on your calculator, that's fine. Remember, we were doing 0 to pi over 2. So maybe like this is pi over 4. This would be pi over 2. We're talking sine of 0, 0. Here's 1 up here. Sine, it's going to be like this. This is going to be like this. So it kind of looks like this almost on your calculator. Okay. And this is the area we were trying to find the area under which we were trying to find the area under the curve. Okay. So what you end up doing most of the time is if you have to do this by hand, it's really like a Riemann sum, but in this specific case, all of your rectangles happen to be the same width. Okay, so it's a little bit easier because the widths are going to be more consistent, so you don't have to do as much work to figure them out. But what you do need to do is figure out, first of all, where your rectangle is going to start and stop, and then write it out. Okay, just like we just did on the last one. All right, so you might want to draw yourself a picture like this. All right, we need 4 subintervals. All right, so going from 0 to pi over 2, we have to fit in 4 rectangles. Let me get another color to do this in. Do blue. All right, so I think everybody would agree we're going to have one rectangle end right here. That's going to be pi over 8. The second rectangle is going to end here at pi over 4. The third is going to be here at 3 pi over 4. No, that's not going to be 3 pi over 4. That's wrong. Pi over 2. That's going to be 1, 2, 3 pi over 8. There we go. And then the last one's going to end right here at pi over 4. Okay, so since it has to be a left endpoint approximation, remember what that means, is that when you draw your rectangles, the upper left of each rectangle has to hit the curve. So I'm going to start actually with this one right here. All right, there's one rectangle. Notice how it's the upper left that hits the curve. All right, the next one is going to hit right there. Then the third one. The fourth one is the one that's pretty much just lying right on the axis. All right, this is actually something, when we're getting ready for the quiz, there was a free response problem that was very much like this, and you had to draw it out as part of the free response problem. All right, so we're still going to do it just like we did before. So the area under the curve is going to be approximate, and we're just going to go one rectangle at a time. All right, so the first rectangle, it's pi over 8 wide, but the height is 0 because it's lying right on the x-axis. Okay, so that's your first rectangle. Second rectangle, this is rectangle 2, right there. All right, it's also pi over 8 wide. The height is being given by the function value at pi over 8. All right, so this is where we can go ahead and do it on our calculator, just like we did the last one. Okay, all right, here's the third rectangle. All right, that's going to be pi over 8 wide. The height, all right, that's given by the function value at pi over 4. All right, so then finally our fourth rectangle, that's pi over 8 wide. And the function value, that its height is this one here at 3 pi over 8. All right, now you all should have written down what the calculator had given us for the left endpoint approximation, but let's go ahead and do it this way, and you should find you get the same thing, because this is really what the calculator's doing when it runs that program, is actually doing this number crunching really, 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 really fast. Okay, so let's go ahead and type that in. I should jot that down. I don't think I have that written down. Just really quick, let me write that down. So, pi over 8. Any question where I got that from?
Miss Henderson?
Yes.
I'm confused on how you got pi over 3 times f of pi over 8.
Oh, that's an 8. I'm sorry. Thank you. Typo. Thank you. I have no idea why I wrote pi over 3. Absolutely no idea. Thank you.
No problem.
Okay, so let's go back to the calculator. Okay, let's clear this out. Under y equals, you'll want to put the sign of x. Let's get rid of that function. You don't have to worry about setting up your window. You don't have to do any of that again. And we'll probably end today with this one. All right, so once you have y equals sign of x, so let's go back, and we're pretty much just going to do, it's just a lot of typing, because I'm paranoid about my, okay, I don't know why that did that. I'm paranoid about my parentheses, so I'm going to do parentheses around all this pi over 8. You could even think of the pi over 8 as the greatest common factor and factor that out. So you could do the 0 plus function value at pi over 8 plus the function value at pi over 4 plus the function value at 3 pi over 8, get that answer, and then times in the end by pi over 8. So there's definitely things like that you can do. It's entirely up to you. Oh, this one was just times 0, because that was the first rectangle, so you wouldn't even have to type that in, really. All right, I'm going to do it the long way, though, I guess. All right, so this is the second rectangle. This is the one whose height was given by the function value of pi over 8. Oh, I forgot a parenthesis. There we go. All right, so that's your second rectangle you're looking at. Plus, all right, here comes your third rectangle. So it had a width of pi over 8 times the height, which was given by the function value at pi over 4. Okay, so all that's in your screen right there is the third rectangle. Plus, now here comes the fourth rectangle, which was pi over 4, or pi over 8, times the function value at 3 pi over 8. All right, so all that right there is the fourth one. So hit enter, and lo and behold, it's the same thing you got when we did the program. Okay, so that might be a really good place to stop before we start taking a look at some application problems of some of this. What I'm going to do is just give you maybe a couple of these to try, just to make sure you're doing, and then we'll do the other ones later. So just literally 2 problems. And I'll be giving you some other instructions to go along with this. So let me go back and get a new whiteboard. All right, so for homework tonight, and tomorrow we should be back in the studio as usual. They were doing electrical work on campus today, so we have no electricity there at all. So if you would just do page 321, number 2 and 4, okay? What I want you to do is use inscribed rectangles. Okay. You decide if it's a left endpoint or right endpoint. All right, just based upon the fact they have to be inscribed. And then you're going to do part of this assignment. I'm going to have you do it on the calculator with the programs. You can decide which program you want to use, either the area program or the int maths. So on your graphing calculator with the program, I want you to do it with like n equals 10, then 50, then 100. All right, and just jot down what you get for the area using each of those number of subdivisions, okay? And then by hand, just like we were doing it before with writing it out, those last 2 problems, do n equals 3, so 3 rectangles.